Hey everyone, and welcome. Have you ever stared at a computer's spec sheet and just felt lost in the numbers? We're always told that a bigger number must mean it's faster, it's better. But is that really the whole story? Today, we're going to peel back the layers and find out what's really under the hood.
All right, let's just jump right in with the big one, the question that's on every single price tag. You've got two processors. One's a 3 gigahertz, the other is 2.5. The 3 gigahertz one has to be faster, right? I mean, it just sounds like simple math.
Well, spoiler alert, nope, it's not that simple at all. In fact, the idea that clock speed is the only thing that matters is probably one of the biggest myths in all of computing. And in this explainer, we are going to bust it wide open.
Okay, so let's really dig into this gigahertz myth. To understand why that one big number on the box doesn't tell you everything, we kind of need to completely change the way we think about what a computer processor is actually doing.
So, I want you to picture this. Your entire computer is a big, busy factory. And right at the center of that factory, there's a super advanced assembly line with this one incredible machine doing all the hard work. That machine, that's your CPU. Its whole job is to crank through tasks to get things done. Now, to really get what's going on, we have to look under the hood of that machine's engine. You see, performance isn't just about raw speed. It's about a whole bunch of things working together. How efficient the machine is, and even what kind of work you're asking it to do in the first place. First up, let's talk about that clock rate, the whole gigahertz thing. In our factory, that's just the speed of the conveyor belt. A 3 gigahertz processor has a faster moving belt than a 2.5 gigahertz one, no doubt. It's feeding tasks to the machine more often. But, and this is a huge but, that's only one piece of the puzzle.
Next up, you've got something called instruction count. Think of this as the factory's to-do list for a given job. A really well-written, efficient program is like a simple, elegant blueprint. It just doesn't require as many steps to build something. A bloated, clunky program? Well, that's a long, complicated to-do list that's going to slow the whole factory down.
And the third piece is called cycles per instruction, or CPI. This is all about your machine's efficiency. How many ticks of that conveyor belt does it take to finish just one task? A super modern, advanced machine might get a task done in a single tick. An older, less efficient one might take 4 or 5 ticks for the exact same task. So, a lower CPI is way, way better.
And here is where it all clicks into place. This is the secret recipe for computer performance. Look at that. A high clock rate is great. It's on the bottom, so it makes the final number smaller, which is good, but it can be totally wiped out by a massive instruction count or a really inefficient high CPI. So you could literally have a processor with a lower clock speed, but a fantastic CPI that runs circles around a chip with a higher clock speed. It's all a balancing act.
But here's the thing. A CPU doesn't exist in a bubble. Even the most powerful, perfectly balanced engine in the world is completely useless if it's just sitting around waiting for parts. The rest of the factory is just as important. I mean, think about it. What good is the world's fastest assembly line machine if it has to pause for 10 minutes every time it needs another bolt? The incredible speed of that machine becomes totally irrelevant if it's constantly being starved for the data it needs to work on.
And this is where the memory hierarchy comes in. It's brilliant. The absolute fastest data is in the registers. That's like the tools and parts already in the machine's hands. Right next to it is the cache, a little bin of frequently used parts super close by. Then you've got your main RAM, which is like the big warehouse for the whole factory. It holds a ton, but you gotta take a trip to go get stuff. And finally, your main storage, your hard drive or SSD. That's the slowest of all, like having to wait for delivery from a supplier in another city.
Any one of these steps can become what we call a bottleneck. It's the weakest link in the chain. If your super fast CPU is always waiting for data to arrive from your slow RAM, we say the system is memory bound. The entire factory's production is limited by its slowest part. It's not always about the CPU. So, faced with this, modern engineers came up with a pretty clever idea. If one assembly line is hitting its limits, why not just build more? This is the whole idea behind multi-core processors. But as you're about to see, even that has its limits. See, if you look at a program's total workload, some parts are parallelizable. You can split those tasks up and have all your assembly lines work on them at the same time. Awesome. But there's always a chunk of the work that's serial. These tasks depend on each other, and they have to be done in a specific order, on a single line. And it doesn't matter if you have 100 extra assembly lines waiting around, that serial part is going to take as long as it takes. And this fundamental limit, this law of the land for parallel computing, actually has a name. It's called Amdahl's law. It's the math that proves you can't just throw more cores at a problem and expect infinite speedups. And this is what Amdahl's law looks like in the real world. You get what are called diminishing returns. Going from 1 core to 2, huge performance boost. 2 to 4, still nice, but not quite as big of a jump. By the time you get to 8, 16, or more cores, the extra speedup gets smaller and smaller because that pesky serial part of the code becomes the main bottleneck. You eventually just hit a wall.
Okay, so far we've been talking almost entirely about the hardware, the factory itself, the assembly lines, the warehouse. But what about the blueprints? The actual software you're running plays an absolutely massive role in how fast your computer feels.
It's simple. Smarter software makes everything faster. A more efficient algorithm can literally slash the total instruction count, meaning the factory has less work to do. A good compiler acts like a master translator, turning the plan into the most efficient machine instructions possible. That lowers your CPI. And smart resource management makes sure the CPU almost never has to wait for parts. And that right there brings us to the final and honestly the most important idea of all. Performance isn't a hardware problem to be solved or a software problem. It's a partnership. They absolutely depend on each other. Think of it like this. The hardware provides the potential. It gives you the raw speed, the number of assembly lines, how fast you can get parts from the warehouse. But it's the software that determines the actual work. It decides how big the to-do list is, how efficiently each task gets done, and how to make the best use of all those extra cores. So, to wrap it all up, true performance is a measure of the entire system working together in perfect harmony. You have to think about the CPU's speed and its efficiency. You need to consider how fast the memory can supply data, the speed of your storage, and, just as critically, the quality of the software blueprint that's running the whole show. It really all boils down to this one simple truth. You can have the most powerful hardware on the planet, but if you run poorly optimized software on it, it's going to feel slow. And the most beautifully written software is still going to get hamstrung by old, slow hardware. The real magic happens when they're perfectly matched. So the next time you're looking to buy a new computer or upgrade a part, I really hope you'll think about the whole factory, not just how fast one little conveyor belt is moving. Think about the efficiency of the machine, the speed of the warehouse, and the quality of the blueprints. Because the real secret to a fast computer is, and always will be, balance.